Another basic rational function is f of x equals 1 over x squared. And so let's go ahead and make a table to see what's going on with this rational function. So go ahead and put value for x, and f of x equals 1 over x squared, and then we have our value for the ordered pairs. So I pick 1. Again, we can't pick 0 because 0 would make this denominator 0. So I pick 1. I get f of 1 is 1 over 1 squared, which is just 1 over 1, which is 1. I pick 2. I get f of 2 equals 1 over 2 squared, which is equal to 1 over 4. 2 and a fourth. I pick 3, and you can kind of see the pattern here. It's going to get very small because it becomes 1 over 9, which is super small. And it gets smaller and smaller. So as the x gets bigger, the y gets smaller. If I pick negative values of x, I get f of negative 1 is 1 over negative 1 squared, which is 1 over 1. So I get negative 1, 1. Do negative 2, 1 over negative 2 squared, which is 1 over 4. Negative 2 and 1/4. And you're going to notice that I will get the same y values here when I change the x sign. Okay, let's see what happens here. 1, 1 is right there. 2 and a fourth would be right here. 3 and a ninth would be right there. And you notice that, again, if I pick any value for x, whatever I pick 4, 5, and so on, it's going to be 1 over that number. It can be super, super small. With y value, can get really small, but it's never going to reach 0. So we can go ahead and extend this here. But it's never going to reach 0. So this value here, y equals 0. Y is never going to be 0. And then if I did negative 1, I get 1. If I do negative 2, I get a fourth. And negative 3, I would get 1 over 9. And you can see the same pattern there. It would never reach 0 because this number would always be small, but would never get larger, or never reach 0. Now what happens if I pick 1/2 for x? F of 1/2 would equal 1 over 1/2 squared, which is 1 over 1/4, which is 4. I get 1/2, 4. Likewise, if I did negative 1/2, f of negative 1/2 would equal 1 over negative 1/2 squared, which is 1 over 1/4, which is 4. If I get negative 1/2, I get 4. If I continue this graph, it would look like this. The x value would never be 0 because no matter what I put here, I can't be 0 because I can't put 0 for x. So I'm going to go ahead and put an asymptote there also. I'll put a dotted line right here. X equals 0 because it will never equal 0. Okay. Vertical asymptotes of rational functions. So we kind of talked about this in the previous two examples. A rational function may have no vertical asymptotes, one vertical asymptote, or several vertical asymptotes. The graph of a rational function never intersects a vertical asymptote. We use a dash line to show asymptotes. I've done that already. How do you locate vertical asymptotes? Basically, you're looking at what x cannot be, and then you would draw an asymptote there. So let's look at example 2. Okay, so here I have the function, the rational function x over x squared minus 9. That same thing as f of x equals x over x plus 3 x minus 3. So x cannot be negative 3 or 3. So the lines x equals negative 3 and x equals 3 are vertical asymptotes. For the graph. So when later on in this section, when we graph this rational function, we're going to draw a dashed line at negative 3, x equals negative 3, and x equals 3, because we do not want our graph ever to have that value. Correct. Okay. And so part B, do a different color here. G of x equals x plus 3 over x squared minus 9. The same thing as x plus 3 over x plus 3, x minus 3. The same thing as 1 over x minus 3. How do I get that? Well, these two factors cancel out. I end up with 1 over x minus 3. So the line x equals 3 is a vertical asymptote. I'll abbreviate vertical asymptote with VA of the graph, or for the graph. Okay. And the last one, h of x equals x plus 3 over x squared plus 9. Well, there's no way that this denominator will ever equal 0. And we talked about that in a previous example. I can put whatever I want for x, and it will never equal 0. So there's no vertical asymptote here. Okay, so on your own, go to the next problem. Go ahead and find the vertical asymptotes of each graph, if any, and go ahead and write the equation for them. Make sure you pause the video and then replay it when you're done. Okay, so here are the answers. In A, the vertical asymptotes are x equals negative 1 and x equals 1. In G, x equals negative 1 is your vertical asymptote. And in C, there's no vertical asymptote. Again, vertical means a line that goes up and down like this. So we're going to have a dashed line that looks like this. Oops, that's not very vertical, is it? Something like this. You know, dashed line, that would be the equation for that line. Horizontal asymptotes. Many but not all rational functions have horizontal asymptotes. While a rational function may have several vertical asymptotes, it can have at most one horizontal asymptote. It can only have at most one horizontal asymptote. To find the horizontal asymptote, you need to have this not memorized. I'll give you this on your exam. You'll have it on a sheet given to you. To find the horizontal asymptote, you're going to look at the degree of your leading terms, and then you can compare the degrees. So I'll look at this in example 3. So example 3 here is my function. If I want to find the horizontal asymptote, I'll look at the degrees of the leading terms. In the numerator, the degree of this x is a 1, and the degree of this is 2. So the degree on top is smaller than the one on the bottom. So if it's smaller, the degree on top is smaller than the one on the bottom, then the x-axis, or y equals 0, is the horizontal asymptote. So the horizontal asymptote here is y equals 0. Because I have that 1 right here, and 1 is less than 2. So we're in this first case here, and it's telling you that y equals 0 is the horizontal asymptote. Part B, if you look at the degrees here and they're equal to each other, then the horizontal asymptote is going to be the line y equals these coefficients here. So the horizontal asymptote is going to be y equals 4 over 2, y equals 2. This is true because these degrees are the same. If the degrees are the same, you can take these two coefficients here and divide them out to get your horizontal asymptote. And in C, if the degree is larger on top than the bottom, that's this case here, then there's no horizontal asymptote. Okay? So let's go ahead and on your own do these 3 right here, and again I want you to focus on the 3 statements up here to define your horizontal asymptote. Go ahead and pause the video and then check your answers. Okay, so here are the answers on your own. In part A, the degrees were the same, so we're going to take the coefficients and divide them out, and then I get y equals 3 because on asymptote. In B, the numerator is smaller, the degree in the numerator is smaller than the degree in the denominator, so we have y equals 0. And then in C, the degree on top is bigger than the degree on the bottom, so there's no horizontal asymptote. Okay. On page 138, what I have here is actually the two common rational functions that we graphed earlier. Remember I told you there's really 6 points on that first one that I want you to plot out, and here they are. The 1, 1, the 1/2, 2, the 2 and 1/2, and so on. Those were the points that I emphasized when I did this example right here. Same example, and I point out these are the points I want you to have on that graph. It's the same one that I have labeled here on the top of page 138. And then the other one I have 1 over x squared, and these are the 1, 2, 3, 4, 6 points I want you to have. Either memorize label. Most of will just memorize these, or just plug in the half, the 1, the 2, the negative half, the negative 1, and then negative 2, and then vice versa here. Okay. So on both of these, they have asymptotes that we're going to go ahead and draw in. They're not drawn in for you here. Here I have x equals 0, and they draw that right. They label it here. And then I have y equals 0 here. They don't label that. Here y equals 0. Here I have x equals 0. If the computer or the potion put it in there. So y equals 0 is this line here. X equals 0 that line. And then here it's x equals 0. Oops. Y equals 0 here. So y equals 0 on this line, and then x equals 0 this line right here. So knowing that, if I want you to graph the original function f of x equals 1 over x squared, you should be able to go ahead and plot that pretty quickly. We've got the 1, 1, and the negative 1, 1, with a half and the 4, with a negative half and the 4, and then we have the 2 and the 1, 4, the negative 2 and 1, 4. So that's the original function. I'm probably drawing my iPad. These are the dots, points I want you to focus on. Now we're talking about transformation. We talked about transformation in the last chapter. If I now have this minus 2 down here and the plus 1 from its original function, this tells me what to do. This tells me what to do. So this down here tells me I'm going to move it to the right 2 units. That's my next step. Take each of these points, move to the right 2 units. When I move to the right 2 units, it becomes 1, 2. It goes right there. When I move this to the right 2 units, it goes 1, 2. There'll be 1 1/2 there. Oh, I'm actually going to make it easier, and I'm going to go ahead and do this as, if we go ahead and put our asymptotes in, this will make it a little bit easier. This is x equals 0. This is y equals 0. Actually, it makes it a big difference to go ahead and shift these to the 2 unit first. So 1, 2. So 1, 2, they'll be right here. So I'm actually getting ready to run out of time, so I'm going to start this in the next video, but this is going to be where I'm going to start off at. And I'll go ahead and stop the video now.